Linear transformation is a function that moves vectors in a very controlled way. Controlled means two rules always hold. First, if you add two vectors and then apply the transformation, you get the same result as transforming them separately and then adding. Second, if you scale a vector and then apply the transformation, that's the same as transforming first and then scaling. Those two rules force a lot of structure. One immediate consequence is that the 0 vector must map to 0. Another is that straight lines through the origin stay straight lines through the origin. So linear transformations don't bend space or tear it. They stretch it, rotate it, shear it, reflect it, or flatten parts of it. Here's the key insight. A linear transformation is completely determined by what it does to a basis. Any vector can be written as a combination of basis vectors. Because the transformation respects addition and scaling, once you know where each basis vector goes, you automatically know where every vector goes. Matrices come from choosing a specific basis, usually the standard one. In 2 dimensions, that's the vector 1, 0 and the vector 0, 1. To build the matrix of a transformation, you apply the transformation to each of those basis vectors and write the results as columns. Multiplying a matrix by a vector is just forming the same linear combination of those transformed basis vectors. So matrices don't create transformations, they record them. Geometrically, you can think of a linear transformation as grabbing the coordinate grid and reshaping it while keeping the origin fixed. The columns of the matrix tell you where the grid's axes end up. Areas and volumes may change. That change is measured by the determinant. If the determinant is 0, space gets flattened and the transformation cannot be undone. If it's non-zero, the transformation is invertible. Some directions behave in a special way. Eigenvectors are directions that don't turn under the transformation. They only get scaled. The scaling factor is the eigenvalue. These directions reveal the internal structure of the transformation. Finally, the same transformation can look like different matrices if you change coordinates. The geometry stays the same, only the bookkeeping changes. That's how linear transformations work. Simple rules, strong structure, and a deep link between algebra and geometry.